we're talking about structure from motion, remember? So we derive all the basic concepts and this factorization algorithm. I just want to review very quickly the main ideas because these are extremely important for your understanding of how you can recover geometry of an object from two-dimensional images, okay? So imagine that you have an image like this. This is meant to imitate a synthetic image that imitates your calibration grid that was part of your project, right? So this is a calibration grid, and I have here 1, 2, 3, and 4 cameras located like this. Now, if I take pictures with these 4 cameras, that's what I'm going to see, right? So image 1 comes from this camera, so it's just basically going to see that plane, the red plane, right? And it's not going to be able to distinguish between these 2 planes that are going to become lines, right? So that's what you see here. But these cameras right here, right, they have a different view like this. And this top camera is going to see something like this, okay? So this is how this is constructed. These are the small p's that gives us the u's and v's, right, of the image coordinates. And I want to recover the capital P's, which are the x, y, and z's that are the three-dimensional world coordinate points, right? So that's a problem that we have, and we have derived this here. So we have our image points that are given on this side times this capital A matrix that corresponds to all the affine cameras that we are using, right, to get the projection for each I-dimensional point, three-dimensional point, onto this M different images that I have, right? And if I compound I put together all the PIs, then I'm going to call this capital P here for all the endpoints. And D represents all the corresponding image points now. So this is the known or the observable data, right? Sometimes called the data matrix. And this is the camera matrix and the three-dimensional structure, right? So the motion and the structure, therefore structure from motion. And we've shown that you can use SVD to decompose this matrix, the data matrix, the only unknown that I have, and then take the first 3 singular vectors and singular values and equals them to A and P, right? So you have this here on top, 2 possible solutions for A hat, P hat. So far, so good? Now, the problem with this is that if we recover our three-dimensional structure with this and we plot it, this is what we're going to see. Now, why do we see this? Because this shape that I have recovered here is actually a fine equivalent to the shape that I really want, which is the Euclidean shape, right? The original shape that I have. So that's a problem. This isn't a fine shape. There's nothing wrong with it. Only that we would rather have the Euclidean shape that we had to begin with. And the reason we have this is because, remember, every point given in this equation is given up to an affine ambiguity. This is the affine ambiguity, right? Which is anything else than, is nothing else than an affine transformation from one affine space onto another affine space, right? So remember, I was showing an ellipse the other day, right? And then I put this 2-dimensional ellipse in 3-dimensional space, and I take 2-dimensional images of that. Depending on the orientation of that ellipse with respect to that other 2-dimensional plane, may actually see an ellipse or a circle, right? And that's the problem, that this projection, defined here as an affine projection, right, which is what it is, then can distort our observation of the object like this. So now I want to go from this that I have recovered back to this, right? So how do I get this? That's a final step I need to solve. So that's what the first thing we're going to do today. So let's get back to the notation that we have here, right? So these are my image points, my three-dimensional points, my camera model, and my three-dimensional points. And this is my matrix Q that is causing all the problems that I have. So since the equation that I solved, remember, is this one, right? Okay. So if I put this together, right? I put this one and these two results in here. This is what I'm going to get. I'm going to get D is actually equal to my M, the real M I want, right? This is the M I really want, okay? Times my matrix Q that has made its way into the system without my approval, and then Q inverse times P, right? So let me call these maybe M prime and P prime, right? For this one here, M prime, and this one here, P prime, okay? Now, of course, if I am in the affine space by itself, there's no ways I can ever recover Q, right? We've seen that because they are affine equivalent, so there's nothing else I can do. What I can do, however, I can add additional knowledge, right, into the system. Things that I know or that I assume to be known, right? Hypothesis, basically, right? Or assumptions. So anyone can tell me of some ideas of what we can add that we may know or assume to know about M? M is what? What does M define? It defines a projection, right? It's the camera model. So can I use one of the camera models that we have defined before and then impose that these parameters take certain values? Of course, right? That's exactly what we're going to do. So we're going to assume that we use one of the camera models. For example, I'm going to use the weak perspective camera model. Remember the weak perspective camera model, which is given by, if you remember, it was 1 over Z. Anyone remembers? 1 over? The midterm is coming up in what? 1 over ZR, thank you. Yeah, very good. And then I had two parameters here, the aspect ratio and the skewness of the camera, K and S. And then I had a matrix and a vector, a 2 by 3 matrix, R2, that defines a two-dimensional rotation with respect to this reference frame, right? So obviously there's no rotation in 3D because I'm assuming weak perspective. I have fixed this reference point. So this is a 2 by 3 matrix. It's nothing else than the first two rows of the real rotation matrix, right? And T2, which is the first two elements of the translation vector, right? All right, that can be solved, but for simplicity, I'm going to simplify this a little more. I am going to assume that my camera, let's say, is aspect ratio 1, meaning that the pixels are a square, right? Can I assume that? I mean, it's a reasonable assumption, right? Now, I don't think there's any camera out there for which the pixels are a square, but it's a good approximation. I can also assume that the skewness of the camera is 0, right? That angle, the cosine of the angle is 0, so the angle is 90 degrees, right? In that case, that would be, the skewness would be 0. And what do we say about the aspect ratio? 1. Okay, so this is the identity matrix, so I might as well just get rid of it, right? And now I have simplified my equation, right? So this is the weak perspective camera model with aspect ratio 1, or unit aspect ratio as we've called it before, and not in the skewness parameter equal to 0, basically, which means that the angle between the two vectors that define the image plane, the physical retina, is 90 degrees. All right. So now I'm going to write, let's say, let me do maybe m hat. I haven't used m hat, have I? M hat is equal to a hat b hat, right? And I want this to be equal to this thing right here, okay? So I want this to be equal to 1 over zr times r2 t2. Now, if you have to remember this in your midterm exam, you can think of a Star Wars, right? It sounds like this, R2, T2. Close enough. Okay. Maybe that'll help you remember. All right, so m hat, a hat, b hat has to be equal to, now, this is a scalar, right? We don't really care about a scalar because our homogeneous coordinate system, even for the Euclidean case, is not going to give us a result up. It's going to give us a result up to scale, so it's not going to give us the correct scalar. So I'm going to just get rid of this. So R2 T2 and A, of course, it's a matrix with 2 rows, right? Let's call it A1 hat and A2 hat. Okay, and what do we know? This A hat and A2 hat have to define a rotation, right? Am I right? These two, so if they define a rotation, they have to be what? What is it? Orthogonal, yes. Orthonormal, very good. It's even better. So I want the inner product of A1 hat, A2 hat be equal to 0. And I want the norm of A1 hat and the norm of A2 hat to be equal both to 1. And here I have a system of equations. So I have my system of equations that I need to solve. Now I can put everything together. So let's see. I have m hat equals, again, a hat b hat, which is equal to my a and b, right? These are the a's and b's that or the a and b, rather, that I want to recover, right? Times my affine transformation, which is given by c d0, a row vector of zeros and a 1, right? Yes? So that means that this m hat is going to be equal to, let's see, it's a times d b0, so ac, and this one is AD plus B, right? Am I right? Okay. And what have we called this first component here? A hat, right? And this one? B hat, right? Yeah. And we have them here in this equation. So now I can substitute this here. So I'm going to have, let's see, A1 transpose CC transpose A2 equals 0. I have then A1 transpose CC transpose A1 equals 1. And A2 transpose CC transpose A2 equals 1. Yep. So this is a system of equations as we have been defining them, right? And if I have enough points, right, enough equations, I can solve for my unknowns here, right? Now, note that I don't have V, although I could recover a B. This is a translation, right? And whether I recover, this object, I recover it here or I recover it here, I don't care, right? I mean, it's the same shape. So translation, I'm not going to be concerned about. But the C, I do care about because that's what's going to give me the Euclidean shape that I'm so desperate to get. Unfortunately, this equation, or this set of, this system of equations, is a nonlinear system of equations, right? So we cannot use linear least squares to solve it, even if I have enough equations. But I can use nonlinear least squares, right? Okay. So let's see. So let me go back to the slides just for a second. Okay, so here's where we were. Now we know how to solve for this transformation, right? These are the equations that we just derived. So we solve with nonlinear least squares. We find a solution for our matrix A hat, and that's what we recover, right? Great. Now, obviously, this is for a synthetic object for which I have taken pictures with an actual pinhole affine camera, right? In reality, these things are only approximations. This is an example, though. Again, this is synthetic images, but still, if I take this certain number of images, 150 images, this is from a video of a camera rotating around an object, and I track a certain number of points, then I can reconstruct the object in 3D like this. This is reconstruction of a face with a small number of points. And I think I have a few more. OK, but this is all right. I'll do that in a second. I'll show you more interesting results in just a second, okay? So let's see one final algorithm to do this. And to my knowledge, this is still, after several years, the best algorithm that you can get or straightforward algorithm that you can use. Question? Oh. And it was derived by a colleague of yours, a former student here at Ohio State, a student in my lab, who is now enjoying life in Zurich, I think, isn't it? So this is called column space fitting algorithm. And you'll see it being called in the literature, people call it CSF for short. And it's very simple, very elegant. So I'm going to use a notation that the paper that I posted in Carmen uses. So I don't want to confuse you. This is slightly different than the one I've been using, okay? So the data matrix is called W. And W, it's a matrix of m by n, right? So W, just to repeat myself, has all the UVs, right, of, or x and y's, if you will, of the image coordinates. So if you use x and y's, it would be x11 and then y11. This would be the first pixel as seen from the first camera, right? And so on. You go all the way to, if I have m, it would have to be m halves, I guess. So x m half 1 and y m halves 1. And if I have n points, I would have 1n and m halves n, m halves n, right? So that is my data matrix of all the image points, right? N points, m cameras, correct? Now, for the affine case, the rank of W, we know is, in the general case, is 4 or less, right? Now, if I eliminate the translation vector, right, if I subtract that translation vector, then it's 3, as we've seen before. But if not, it's obviously 4, because it has a translation too. OK. And our equation, in the paper, you will see this notation. The data matrix is equal to the camera matrix M, and the shape of the object is given by S. OK? The matrix S. And of course, M has to be a matrix of M, because I have M cameras by R. And S has to be, what do we say? N, right? R by N. OK. So let small w, w vector, j, define in, say, m sub j dimensions in the real domain. Let this vector be the entries of the jth column of W. OK, so W is going to have this one here. It's going to have the first column, right? I'm going to call it W1, W2, and so on. But, wait for it, this is such that this is such that I am not using all the m entries of that column, right? This column has m entries, correct? I'm only using the ones for which the points are visible in that image. Because, in general, in a structure from motion, right, when I take a picture of this object from this point of view, this point is visible, but this point is not. When I have the camera on the other side, this point is visible, this one is not, right? Now, one trick that people think they can use is you can just put zeros in the location of the missing points. But the 0 has a meaning, right? And that point is not visible. Doesn't mean it's 0. It means that I don't know what the value is. So what you do is you write this vector without those entries. So now mj is going to be smaller or equal than m, right? Now, to apply this to my matrix M, right, or the corresponding mj, I'm going to use an identity matrix that I'm going to call pi j. And this identity matrix is called the row amputated identity matrix. And this is nothing else than the identity matrix that we all know and love, right? With diagonals all ones. But I eliminate the rows that I need to eliminate in that vector Wj, such that if I multiply this by Wj, the original of the matrix capital W, I obtain the vector without the missing entries, right? Okay. So now I can define with this, I can define my Wj, right? Where is my equation? Right here. This equation right here, I can define it as each column that has been amputated in the positions of missing entries is equal to this new capital Mj times the corresponding shape that it can recover from these known points. Okay. And look at this, because obviously this is super fantastic. This Sj, right, which is what we want to recover, my shape. This is given by, let's see, I need to move this to the other side. This is not a square matrix, but I can invert it with, what have we done before to invert this matrix? Pseudo-inverse, very good. So this is equal to the pseudo-inverse, let me call it Mj star times Wj, right? And this is going to be given in R, where Mj star is the pseudo-inverse. Okay, so we're almost ready, or we are ready to define our criteria, our optimization function, so-called objective function. So the function that I want to minimize with linear least squares, of course, right? My goal to optimize a function with least squares would be 1/2 the sum over j of, all right, bear with me for a second, the identity matrix minus Mj pseudo-inverse times Wj, and I'm going to use the Frobenius norm squared. Okay? Now let's see what this means. So look at this equation for a second. Can anyone tell me what this equation represents?
The projection, right?
The projection of what? Very good.
The projection of M.
Not M. M, it's a projection matrix. You're very close.
It's a projection of S to W.
All right, someone else? So you're close because of this, right? What is this? This is W. I projected onto that in pseudo-inverse of M. That gives me the shape, right? And then if I project that shape onto the space, or the space defined by M, what am I doing? So this, I'm going from, what's W? It's the observation, or the data matrix, right? So if I do this multiplication, I recover the three-dimensional points, right? The shape of the object, right? And now if I project these three-dimensional points back with M onto the image again, right? So all this is doing is taking the image points, reconstructing them in 3D, and then projecting them back onto 2D, right? And I want to know if this is similar to just keeping the original image points, right? So if that matrix is correct, then reconstructing it in 3D and reprojecting it back onto 2D should give me the original 2D, right? That's called the reconstruction error function. And it's used throughout image processing and computer vision. This is a fundamental objective function. People use this constantly, okay? The reprojection error, you can call it. So here's the summary of the algorithm. Let's see, actually let me do it here. The algorithm just has a few steps. First, we need to have an initial estimate for m, so you just initialize m. We need a scalar. And then what we're going to do is we're going to do a for loop where we compute the gradient, remember? The gradient G, right? The Jacobian J, and the Hessian H. And then what we're going to do, we're going to compute an increment for m that, remember, is H, the Hessian, plus delta, that's our constant, times the identity matrix inverse times the gradient, right? And I'm going to then modify m by subtracting this increment. And usually what you do here, you orthogonalize the result that you get, because sometimes when you use gradient descent like this for nonlinear least squares, you end up with things that are not perfectly orthogonal, right? And you know that this matrix has to be orthogonal, so you can orthogonalize this. And then you do that until convergence, meaning that you're not making any progress, right? So let's see this again. So here's what we have, right? We have a three-dimensional rigid object, and we move the camera around it, so points become occluded as we move around this, but other points become visible. And these are the equations that we have derived here, right? So this is the original equation of the shape is the pseudo-inverse of m times w, and then we can define it for each row, which gives us this nice objective function here. Okay? These are the derivations that I didn't do on the board, but you have them here for the first and the second derivative that you need to compute the gradient and the Hessian matrix, and then obviously, the Jacobian matrix, and then obviously the Hessian, which is the Jacobian transpose the Jacobian. Okay? And these are the details of the algorithm in case you want to try it. Now, if you want to try, there's a MATLAB version of this algorithm on our website, in the website of my lab. So you can just go there, go to the tab Downloads, I think it's called, and there is a code for this algorithm. So you can just download it and test that. And here are some results. So this is a toy dinosaur It's not a real dinosaur. We couldn't find a real one. All right. There's someone had a toy dinosaur, put it in what's called a rotating table, and this is nothing else than a small, it's typically a circular table that just rotates, and it's used to do ceramics and things like this, right? People put it there, and then while it rotates, with a camera, static camera, you take pictures or video, right, which is consecutive pictures, and you see the object rotating. And then you do point correspondences. So this is the cloud of point correspondences. There are a lot of noisy points, as you can see. And then from this, you can recover the 3D structure. This is the M matrix that you recover with this algorithm. This is what you recover with other algorithms that just it's messed up. This algorithm recovers this. You see the outliers, the errors of the corresponding points here that are out here. But this is the camera matrix that tells you how each camera correspond to each other one, right? Where's the position? So it defines the rotation of the object, obviously. This is with a teddy bear that is moving. It's I don't know if you can see that. There is right here, there is I don't know if it's a plastic or a cord or something that is sustaining this, and it's bouncing or balancing around a little bit, moving. And this is the motion that it's defined. So this is the motion, and this is the shape that you recover, the 3D shape. This is really powerful because you can now, from a set of images, recover the 3D shape and render new images. So here's an example with that dinosaur, right? You can generate a three-dimensional version of the dinosaur, and now you can just place it in movies, in commercial ads, in TV, and that's actually what's used, right, in all these entertainment applications. These are some examples. I don't know if that's going to play. No. But there are very serious applications as well, where it's actually used in surgery to actually know exactly where things are in human body when people want to operate on them. All right, I have a few other things here for you to look at if you're interested. These are things that we cover in detail in computer vision. I do not cover here, but as I said, in computer vision, we go into the projective space, which is really cool. And projective transformations, as says here in the slide, are the most general, and we are all familiar with them because obviously that's what a 2D picture of a 3D world is. It's really a projective transformation. Affine, remember, is a particular case of the projective space. Now, the difference between affine and projective space is that in the affine space, we go somewhere, say that this is a projective space, this whiteboard, it's a projective space, okay? And now I come here in the projective space and I say, you see this line right here? See this line? I'm going to call this line the line at infinity, okay? And when I do that, boom, that's my affine space because that defines parallel lines, right? What are parallel lines? Any two lines that cross this line at infinity, right? These two lines are parallel, right? That is the definition of parallel lines, that they cross at the line at infinity. And we saw that when we were talking about the horizon line. Remember the horizon line? The horizon line is nothing else than the line at infinity. Okay. And then as we have seen today, Euclidean geometry or Euclidean transformations is a particular case of affine, right? So we can add constraints to go from affine to Euclidean, right? So the object that we've recovered the shape, but we've recovered the shape up to an Euclidean transformation, right? We didn't know the translation, the scale, or even the rotation, right? I may have recovered the object in this orientation or that orientation. It's up to a rotation. It's part of an Euclidean transformation, right? So that I can never recover with what I've described today. So remember, we're using homogeneous coordinates. So points like x, y, 1, x, y are described as x, y, 1, where 1 is a homogeneous coordinate. And therefore, this is defined up to a scale k, x, k, y, k. It's just basically the same point. And x, y, 0, those are the points at infinity, right? Those are the points that define the line at infinity, precisely. Points at infinity are not different than any other points. I know that it sounds weird to us because we're just so used to Euclidean geometry, but points at infinity just have the homogeneous coordinate 0 equal to 0, and that's it. They're points like any other point in the projective space. So there's nothing different. Points at infinity may not be preserved. Obviously, the line at infinity can change. Since points at infinity are only an accident of our notation, we can say that all points are created equal, meaning that this is just our choice. In the same way that we can choose a coordinate system here or here, right? We can choose the line at infinity here or there. It's the same thing. What else? Any two lines cross at the line at infinity. We've seen this. This is a finite space. Any projective transformation that maps the distinguished line. What's that? All right, I'm not even gonna get there. Now, in Euclidean geometry, shapes may not be preserved by affine transformation, as we have seen, right? That's what we just solved today. But as I mentioned before, the concept of a circle does not exist in affine geometry, but does exist in Euclidean geometry. And you can also use that knowledge to recover the Euclidean shape. So today, I have used the camera models, the weak perspective camera model, to recover the Euclidean shape. You could also use the fact that circles are circles and ellipses are ellipses to recover the Euclidean geometry. So here's an example of that. The equation of a circle in homogeneous coordinates, remember we did that here in class. So if you have x, y, w, it would be x minus aw squared, right? This would be the equation that we derive here in class in homogeneous coordinates, right? And here that means that the circle is centered at AB, right? Or in homogeneous coordinates, AB1, right? And now, what do you have? Now, you have this x, y, z point, right? And if this is equal to 1, either plus or minus I, 0, these are the solutions of this equation, right? They are complex solutions, but these are the solutions for the circle, right? So you can actually use that solution to define circles in homogeneous coordinates. And that's how you can actually find the Euclidean geometry. Okay. These points, by the way, are called the circular points. That's what defines circles. Okay. You have a few other things. And maybe I'll talk very briefly about Brainsack. Just in case you want to apply this in the real world, I think that this is useful. So until now, we've been using linear least squares and maybe nonlinear least squares to solve our problems, right? But the problem with linear least squares and nonlinear least squares is that a square part of least squares, right? Which means that my function, remember my function f of x, it's equal to x squared, right? And what does this mean? That means that if this is x and this is x squared, that I have a function that looks something like this, right? Now, the problem with this is that if I have that much of an error, right, say this much, this is how much effect this error has on my equation, right? On my final result. But if I have this much of an error, this is how much effect it has in my solution, right? So it's exponentially more important. And that's problematic because if I have a measurement in my image or in my equations, like what I was showing you with that dinosaur rotating, that there were points outside the actual dinosaur because you think that there is a point there, but there isn't, just misdetection, then that is going to be out here and it's going to create a lot of problems, right? These are called outliers because they are points that are not what's called inliers, which are the points that are part of the solution of the hyperplane solution that you're looking for, right? So it turns out a very simple, I mean, this is one of the simplest algorithms you'll ever see out there, a very simple algorithm that generally works to solve this problem, and it's called Brainsack, and it comes from random sample consensus. And let's go through it, just a few steps, very, very simple. If you actually go to the original paper that describes Brainsack, it's just almost like an afterthought in that paper, right? The authors of that paper didn't expect this method to become popular or anything. It's just working on something completely different, and they had the problem of outliers, so they said, oh, to solve the problem of outliers, we're going to use this trick. And now no one remembers what that paper is about, which is not about Brainsack, but everyone uses Brainsack. So you never know, right? The point is you never know what's going to outstand the test of time. So the main idea is to randomly select a set of points, right? So remember in the linear least squares problem, like in your homework, you had, say, in 2 or 3 dimensions, you had the number of points, right? And what Brainsack does, it selects a subset of these points randomly, completely randomly. Just select randomly a set of those, and then use that random selection to find your least square solution, okay? Now with this least square solution, you get a model, right? A solution. Now once you have that model, that solution, you can compute, let's say that my model gives me something like this, okay? Then you can determine which of these points belong to that model and which of these points are not defined by this model, right? They're inconsistent with the model. And then you use the points that are consistent with that model, right? They're called inliers, to recompute the solution. And the ones that are inconsistent are called outliers, and they're no longer used in the process. And you keep repeating this until there is consensus, right, with all your possible solutions. So this is, for example, an example of linear least squares applied, like in your homework, to the detection of a line, right? So you want to find a line here. There is, as you can see, a number of inliers that do define a line, but a number of outliers that would prevent me from finding that line. And Brainsack just finds it. Generally, right? Obviously, you can be very unlucky, and your random selection of points may skew you toward a bad solution. But in general, that will give you right solution. I've added here the MATLAB code, just in case you're interested in implementing this. It's pretty straightforward. It's in the slides. You have it in Carmen. You have it in YouTube in the slides of the video. So that allows you to find point correspondences for images, right, very reliably. And that allows you to then recover the shape in 3D, for example, using a structure from motion as we've seen here. These are more examples of point correspondences that you can find robustly with Brainsack. And so you can see here which are the inliers and which are the outliers, right? So there's a point here that is not in here, right? And so on. So you get the idea of how this works. All right, I give you here a couple of books in case you want to dig deeper into these topics. They're both excellent books. Now, if you hate me because of all the math that are involved in all this topic, you should not. You should hate this guy who is the original person to put emphasis on all these techniques for your. All right. Any questions? Yes.
On Brainsack, how do you decide on the marginal error to detect the outlier?
Very good question. There is no easy solution to that. Yeah.
Does
Yeah.
it follow any particular distribution or something?
You could define it as a distribution, but you don't have to. Right? This is up to you. You could compute the distance, the orthographic distance, right? You could compute the, depends what your model is defining. If your model defines the line that I was showing here, right, use the orthographic distance, right, the orthographic projection, that as the distance to compute inliers and outliers, and then have a threshold to determine what's an outlier and what's an inlier. But that's up to you. Brainsack is just an approach that tells you select points randomly, compute your model, and then see which points fit into that model and which ones don't, right? How you want to define that model, that's up to you, right? Is it going to be a line, a hyperplane, a distribution, a what have you? That's completely up to you. More questions? Nope. All right. Let's move on then. So this is basically the end of geometry. And our next topic is going to be radiometry. This is the second of three main topics that we have in the course. So geometry was a summary of everything that has to do with the structure and motion of the object. Oh, actually, I do want to show you something else. Hold on. Before I move on, I really want to inspire you, so I'm going to show you something else. All right, give me just a couple minutes to start this up. All right, so let me turn that on again. Sorry about that. So this is an application of a structure from motion from a research group at Microsoft that they did a few years ago. And here's the idea. They call it building Rome in a day. So if you can Google this or actually go to YouTube, and you'll find all the videos. Here's the idea. There are a lot of tourists that go into Rome, right, or any touristic place, right? And they all take pictures of the same monuments, right? That's the same as having multiple cameras or the same camera moving in a space around the same object, right? So sounds familiar? Structure from motion, right? And most people these days, beats me why, they want to tell the world that they've been there, and they post their images online. So you can just go online and take, thousands of images of St. Marcus Square or what have you, right? Of the Colosseum in Rome. And then you can use all these pictures to recover both the position of the person that took the picture in three-dimensional space and the three-dimensional structure of the object. Okay? I'm going to show you a few examples of what they got using this. This is real data, right? All these triangles that you see here, all of those are cameras. These are all the cameras that are taking all these pictures. Spectacular. Huh? Here's another one. Oh, that's probably the same one. All right, hold on. No, that's another one. Let's do the Coliseum. That's a Trevi fountain. That's the Coliseum again. And again, the triangles are the simplices here are the cameras. All right. Hopefully that you found this pretty cool. This is something you can now do. Right? You just need some computational power to analyze all these thousands of cameras, but to create this huge matrix. And they had a paper at CVPR some years ago that actually show how to do it in real time, right? Well, in real time, a reasonable amount of time, I should say. Yes?
So when you talk about the structure from motion, the one thing you need to do is to find a point correspondence. But,
yes.
Like if you have thousands of cameras, how can you quickly find it?
That's a whole different problem, yeah. And that is what computer vision does, yes. Okay. That we're not going to discuss this in image processing. That's a computer vision problem. Yeah, very good question. Anything else?
If you have thousands of cameras, different cameras, how to handle with the different intrinsic and
well, you can still assume they are all either affine or weak perspective or what have you, right? You can, right, or projective. You can also use projective cameras. And again, we're not going to cover in detail projective space. I give you references of 2 books that cover this in detail. And I do cover this in some detail in computer vision if you're interested. There's also a course here in another department on photogrammetry that will probably cover this in detail, I assume. So, I mean, this is a whole research area, right, on how to do these things. Yeah. All right, so we're moving on to radiometry. Now, geometry was a study of the shape, of the three-dimensional shape of the objects, the camera models. Radiometry is the study of light. Okay, so which is the other component of the image that we're interested in. And before we can do the same that we have done with geometry, which is define these beautiful algorithms. So in geometry, for example, we've talked about 2 types of algorithms, stereo vision and structure from motion, right? In radiometry, we're going to see an algorithm that's called shape from shading, which allows us also to recover the three-dimensional shape from the actual radiometry in the image, okay? But before we can do any of that, we need to define the basic notation and methodology as we did for geometry. So we're going to spend maybe a lecture or 2 describing all these things. The more we cover, the more that we can add into the midterm, right? All right. Now, if you're out and walking during a sunny day in the middle of the summer, when is it hotter? When do you feel the heat most? Generally speaking, obviously. Is it 7 a.m., 7 p.m., 12 noon, right? Why would that be? And thereabouts, not exactly 12 noon because we're not at the same 12 noon at the sun, but you know. But why is around that time the hottest? The sun is overhead, right? When the sun is right overhead us, right? Then we feel the heat more than when it's at an angle. That's interesting. Let's think about this for a second. So if I'm here on this plane, right? This is me in the summer, maybe wearing shorts. Okay. And now, if the sun, excuse me, if the sun is right above me, I feel the heat more than if it's at an angle. Right? Whoops. Let me make this symmetric. Right? So this is worse than this. And the reason is because of the so-called foreshortening. When a light source or a point is seen from an angle from another point, right? There is an effect called foreshortening, which means that, you see here, the light just hits straight me on, but here it hits me at an angle, right? And there's actually less energy that reaches me. Let's see if we can define this effect, this foreshortening effect. All right, as always, please look at the slides for the drawings. I'm trying my best. So let's say that this is a surface, right? A bended surface like this one, okay? And I'm interested in a point, a three-dimensional point here on that surface P. And I have a light source somewhere in the world, right? And I want to see what is the foreshortening that I have at that point with respect to the light. How am I going to measure this? How about if I do this? What I'm going to do, I'm going to take a perfect sphere, right? Just a sphere. I'm going to cut it in half. I'm going to take the top half. That's called a hemisphere, right? And I'm going to center it and place it here at P, center at P. So this is what I'm going to try to draw. So I'm going to have this three-dimensional sphere, something like this, okay? Okay, so this is my hemisphere, center at P. Now the light source, it's somewhere out there, right? And if I were to draw the vector that connects point P to the light source, that's going to pass through a patch, a differential of a patch, right? The differential of an area right here on the hemisphere. You see that? Right? It's going to cross that. So I'm going to call this that differential of a patch. Let's call it differential of theta and differential of phi, right? To define the angles, the two angles, phi and theta, that define that vector in three-dimensional space, right? So for example, let me draw here my coordinate system. Now my coordinate system, the origin is centered at P. And if I have that vector here, right, that would be the projection onto that plane, x and y plane. So that would define my first angle. And then that other angle right here, it's theta, right? So theta and phi, right? You see how this works? And this is that differential that defines that patch. Now this is called the solid angle. Extremely important concept that we need to define. This is the solid angle. We can say that you have the solid angle that the source, by the source I mean the light source, maybe the sun, okay? The light source subtends on that hemisphere, on that point, okay? So far, so good? Okay, so let's see if we can compute this. I'm going to do, because working in 3D it's a little hard, let's cut the cross section of this, okay? So I'm going to cut a cross section such that this, right, is just a cut, right, of that hemisphere, okay? And then maybe the origin is here. And now what I'm going to do, I'm going to draw this differential of the angle. Now this is the vector that connects me to the source, okay, the light source. And this defines the differential of the area that I'm interested in, right? Just tiny differential. Okay. So to compute that area, I need a line, right? The line that projects here, that defines that little curve, right? Because this is a little curve, I can approximate it with a line, a differential of a line, right? Let me call this a differential of a line dl, maybe. Okay. Now, what I'm going to do, I'm going to compute this. I'm going to do the following. Let's start with this line here. And that middle point, actually that's not very middle, is it? Okay, that middle point right here. So let's say that this is of length L. So this portion right here is L over 2, and this is L over 2 as well, right? And now if I have this other orthogonal line here, I can define my angle theta 1. And if this is theta 1, what is this? Theta 1 as well. Very good. Excellent. Now, this one that I'm looking for, this is, of course, orthogonal to the vector, right? That has to be orthogonal. You agree? And anyone can tell me what this angle is? If this is 90 degrees, this is theta 1 as well. Okay. So I have now, I can write that my differential of the angle times the cosine of theta 1, right, is divided by, wait, we need to divide this by, because I'm assuming that all these derivations, assuming this is radius equal to 1. I don't know what the radius is, but I can simplify it by dividing by the radius. Then I'm fine, right? Okay, excellent. So with that, what we are going to do is we're going to define our differential. So this is in obviously just 2D. If I go into 3D, I'm going to find the differential of the angle as that differential of a line times the cosine of that angle theta 1 divided by r. Okay. Now to compute the curve, what can I do? I can make these differentials tiny, 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 tiny small, and then integrate, right? And that's my curve. So that is how I can compute the solid angle. Okay. Now, because everything I have done here is in 2D, I can extend this to the idea of the solid angle. Let me call it differential of W, where now instead of a line in the hemisphere, I'm not going to use a line in 3D. I'm going to use a plane, right? So all I need to do is change this for a differential of an area. Differential of an area, still the same, the cosine of my angle, and I need to divide by r squared to normalize for the radius. Okay, so we can use that to define the solid angle. Now, it's called the solid angle because this is in 3D compared to the angle in 2D, right? So it's just a generalization of the concept of an angle. Okay, what else? It can be shown, you may want to do this to make sure that you understand this, and all this is in the book, by the way. Please review it because it's important, but you can redo this derivations that we just did here and write this down instead of with respect to the cosine of the angle, with respect to the sine, right? I mean, same thing. And you will see it's the sine of theta, and then you have differential of theta and differential of phi, right? And with that, you can also compute the differential of the angle, the solid angle. More things. Radians. So we know now what the solid angle is, and we can use that to define or to interpret the foreshortening that I have, right? Which is defined by that solid angle in 3D space. In 2D, it would be defined by the angle, but in 3D, it would be defined by the solid angle, right? But in order to understand what's happening, I also need to define radians, okay? See what the definition of radians is. The appropriate unit for measuring the distribution of light in a space. So it measures the distribution of light in space. And is defined as the power, or I should say formally defined, as the power, you can interpret the power as the power is, let's see, the amount of energy per unit time, right? Or per differential of time, if you prefer, right? That's the power, correct? Traveling at some point in a specified direction per unit area perpendicular to the direction of travel per unit solid angle. So let's decompose this if we can understand what this means. We have, let's see, the power, again, this is the amount of energy per unit time that is traveling at some point. This is our point, P, right here, right? What else do we have? At some point in a specified direction, right? This is the direction that it's traveling in. And per unit area perpendicular to the direction of travel, this is the unit area that's perpendicular to this, which then can be normalized because it's this surface right here, per unit solid angle, which remember, it's just projected onto the hemisphere, right? That's what the solid angle is used for. Okay, great. So let me call this the radians. We are going to call it L, capital L. And we're going to have L as a function of the point. Obviously, if I change the point, I change the radians, right? The radians I have at the point P is different than the range I have in another point Q, right? And it also depends on the angles phi and theta that define that solid angle, that direction of travel, right? So I'm going to also have to add phi and theta. Sometimes you will see this written as LP of vector V, where V is the vector that defines the direction in three-dimensional space. It's the same thing, right? Now, we're going to assume a couple of things. We're going to assume that light travels in straight lines, right? So we're going to assume that photons go in straight lines. Now, of course, light is also a wave, which, it's a problem. And obviously, we are going to ignore quantum mechanics. And if you're familiar with the double slit experiment, right? You will know that I don't really know what happens between point A and point B. And in fact, this is a fascinating area to get to know if you haven't, because it's one of the most fascinating experiments I have ever heard of, right? The double slit experiment, where you know what I'm talking about. You have a machine that emits, say, photons, right, of light. And then you have a screen where these photons are imprinted, right? But in between them, you put a screen that has just two small bars. and then the photon can either go through this bar or through this bar, right? And then if that were the case, the image that would be imprinted would be 2 lines at the other side, right? But that's not what you see, right? What you see is a double Gaussian distribution, right? And that's because light is a distribution, right? It's a wave and it travels. So it's really, physicists have invented every possible mechanism to try to uncover what is going on. And to this day, they don't know, right? So for example, say, wait, does this mean, because obviously my understanding of the classical interpretation of quantum mechanics is that the light goes through both the slits at the same time, right? Otherwise, you would not get this interference pattern. But that just doesn't make an intuitive sense. But you can determine whether this is true or not by putting a red filter and a green filter on each slit, right? And then you will see which area is red and which area is green on the other side. But it turns out that when you do that, because you're measuring what's happening, then you do get the 2 lines, right? The interference pattern disappears. Whoops. It's incredible. And you can go on like this forever, right? It makes for a nice coffee discussion if someone is interested. All right. So we're going to assume that light travels in straight lines and make everything super easy on us. And what else? And we are going to assume that our light does not interact with the medium through which it travels, okay? Now, remember Snell's law, right? Now, the medium does matter, right? People think that light, so light travels in a constant velocity, right? Right? You all agree, right? The speed of light, it's constant, no matter what. But it's constant in a specific medium, right? Light doesn't travel at the same speed in vacuum that it travels in water, right? The difference is very small, but there is a difference. A way to test this is you could have light travel in a medium that has been cooled close to absolute 0. You know what absolute 0 is? Okay, you know what temperature is. Temperature measures not how hot things are, although that's how we call them, but how much the particles of a medium move, right? The faster things move, the more temperature you have, right? The hotter they are. So you can calm down the particles. That means that you cool them down, right? And that changes the medium. Now, there are ways of cooling things so far down they're almost at absolute 0. Absolute 0 means particles are at rest. Right? There's absolutely no movement. If you take something that's very close to absolute 0 and you pass light through it, then the velocity changes dramatically from our environment, our medium with air, which is a good approximation of vacuum, as we've seen before, and that medium of really low temperatures, right? And it's so fascinating to see this because say that you shoot a laser into this and you see the line of the laser. Let's say that you shoot just a tiny length of laser like this, right? And then it travels like this. And then as it enters the medium, the front part starts to slow down because of the change in medium. And it slows down so much if this medium is cold enough that the back part basically catches up with it and it becomes a point. And it travels like a point until the very end when it starts separating again into a line, and then it just goes on, right? So obviously there are all these different effects, physics effects, that we can safely ignore, right? We're never going to observe this. Of course, if you ever work in an application in, say, the Large Hadron Collider or somewhere else in physics, then be aware that you cannot use these equations. But if you're just using regular cameras, phone cameras, or good professional photo cameras, right, or video cameras, we are safe to assume that all these things do hold. All right? Okay, what else? Oh, it's time. All right, we'll continue this next week. I'll see you then.